All right, part C of the study team test. A statistics class reports the following data on gender and eye color for students in the class. And you can see that we recorded both gender and then eye color, and we had both blue eye was a possibility, brown eye, and then green/other. And you can see we've got the marginal values off on the side here, the totals. And then the totals for these columns also. And I can tell from this that this class had 64 students in it. And if I was to add the boys and the girls up, 32 plus 32 is 64. That sums correctly. And then blue eyes, 36 plus 10 would be 46. And then 46 plus 18 would be 64. That adds up as well. So the first question I have, it says, what percent of girls are blue-eyed? So we're only looking right now at this column, or this row actually, for girls, right? We're just looking at this. So because we're specifically saying which percent of the girls are blue-eyed, we're focusing on this girl row only. And the number of girls that had blue eye was 16, and there was a total of 32 girls. So we're looking at 16 out of 32. It does ask us to express that as a percent, so I would say, well, that is 50% of the girls are blue-eyed. The next one says, what percent of boys are green/others? Okay, so in this case now we're asked to focus on just the boys. So we're looking at this row of boys, and it says what percent of the boys are green/other. And you can see that there's a smaller number. No, there's actually an equal number of boys. There's 32 boys also, but only 6 of them out of the 32 had green/other. If I do that, I get, I think, 18.75. I'll just write that down. That's 18.75%. You could record that as 19%, or actually 18.75. 2 decimal places is fine. If I really care, I'll ask you to round to a certain number of decimal places, but that's fine. Okay, let's do question C. Says what percent of students? So now we're talking about all students are brown-eyed boys. Oh. So what percent of everyone, and so this is my entire population, there's 64 people. Out of these 64 people total, what percent are brown eyes and boys? So let's see, brown eyes and boys are just these 6. Right? There's only 6 that I could say are brown eyes and boys. So I would say this is going to be 6 out of 64, which ends up being about half of the previous percent, right? So I'm going to write this down as 9.38%. And actually, let me just check that arithmetic real quickly. I don't know why that bothers me. 6 divided by 64. Yeah, if I move the decimal over to, yeah, that's fine. 9.38%, or you could keep the 5 there, but I think that's fine for our purposes. And then finally, what percent of blue-eyed students are girls? So this is different. Now what we're talking about are just the students that are blue-eyed, and I'm confusing by using a green highlighter, but this is the column we're looking at. It says what percent of blue-eyed students are girls? So if you look at it, there are 36 students that are blue-eyed. There are 36. And I can see that 16 of those 36, 16 were girls. So 16 out of 36 of the students were blue. 16 of the 36 students who had blue eyes, 16 of them were girls. So I would say this is about 44.44%. All right, let's move on to question 2. It asks for a flowchart proof. There's a couple of things that are given. And when I see, for example, that I'm given congruence of things, right, I don't need to do anything to establish that congruence. That's done. This is a little different, right? I'm told that these angles are a certain kind of angle. I'm told that they are right angles. And in order to claim that they're congruent, I need to say that they the definition of congruent angles is that there are two angles that have the same number of degrees. Well, it's obvious that right angles have the same number of degrees, but to make this flowchart proof completely, flow, I guess, I would probably start with something like, hey, angle A and angle E are right angles. Great. I could say angle A and angle E both measure 90 degrees. And that's because of the definition of what is a right angle. And then I could say, oh, therefore they're congruent. So when I look at this diagram, I'm pretty sure that I've got, here's a congruent angle. This angle goes with this angle. And then I've got a congruent side because they're giving me that AC, this side, matches up with this side. So then the last thing is this angle. So I'm going to be getting these triangles are congruent by, I believe, angle, side, angle. So to do that angle, side, angle, couple parts, we're going to need to have a pair of angles. We're going to need to have some congruent sides. Then we're going to need to have another pair of congruent angles, but these are a little problematic. These require they require the two right angles, which give me the 90-degree angles. Since they're 90-degree angles, they're going to be congruent. And then I can flow into my final step where the triangle is congruent. So I think this is the basic structure of this proof. I think that these are going to flow to here, to here, to here, to here. This is going to be one of the things. That's going to be a pair of my angles. This is going to be the pair of the sides, and this is going to be the other pair of angles. So this is pretty much the structure of this particular flowchart proof. Let's go ahead and put the details in. I guess let's start with this one that's, I don't think it's complicated. It's just a little tedious, I guess. So I'm going to say angle A is a right angle, right? And angle E is a right angle. I'm sorry. I did not want to make a triangle or whatever. That is a right angle. And those are both given facts, right? If you look at the proof at the beginning, it says, hey, those are right angles, right? Given. Okay, next. The measurement of angle A is 90 degrees. The measurement of angle E is 90 degrees. What is that? That's the definition of a right angle, right? If you've got a right angle, it's got 90 degrees in it, right? So this is the definition of a right angle. The question is, are A and E right angles? Well, yeah, Mr. Roberts, you're not paying attention. Clearly, this flowed down from this way, right? So they're right angles. Therefore, they measure 90 degrees. And look, they both have the same number of degrees in them. That's convenient because it turns out that's the definition of congruent angle. So now I can say that angle A is congruent to angle E. Why? They fit the definition. It's the definition of congruent angles. Two angles are congruent if and only if they contain the same number of degrees. So it's a little tedious, but I go from right angles, which are angles that measure 90 degrees, and since they both measure 90 degrees, they are congruent, okay? And then the other thing that I have here is I've got that segment AC is congruent to segment EF, and that's super simple. That was given. The other thing that was given was that angle C is congruent to angle F, again given, VEN. So I'm all set up here. I'm ready to say these triangles are congruent, right? Triangle ABC is congruent. Let's see, is that the right angle? Right direction. We went from A to B to C, okay? And that goes with E to D. Yep, that's perfect. That lines up very nicely. Triangle E to D to F. And these are congruent by angle, side, angle. That's the congruence condition that is met. All right, that is the completed flowchart proof. You can see everything in one screen right there. All right, let's go to the back of page C. On the back of page C, it says, hey, here's a sequence. Give the first 4 terms of this sequence. So terms of a sequence are we want to know the first term, the second term, the third term, and the fourth term. And these are the term numbers. So these are what I'm feeding in for n. If I write this a little bit larger, so I've got -2 raised to the some box, right? -1, n minus 1 power. If I put a 1 in there, right? Well, 1 minus 1 is 0. -2 raised to the 0 power is 1. The first number of my sequence is the number 1. Okay, let's put in the number 2. So if this is a 2, right? 2 minus 1 is 1. -2 to the first power would be simply the number -2. Fabulous. Let's change n to 3. 3 minus 1 is 2. -2 to the second power, let's see, -2 times -2 would be +4. Okay. And then finally, I'll put in 4. I've got -2 to the third power, which is -2 times -2 times -2. -2 times -2 is +4, and then a +4 times another -2 would be a -8. So those are the first 4 terms of my sequence. I was given the explicit formula there, and basically I'm just putting in the term number that I want. I put in 1, 2, 3, 4 to get the first, second, third, and fourth terms of that sequence. The next sequence, it's nice to see this sequence is written using recursion, and if I read this correctly, it's telling me the first term is the number 6. So this subscript tells me the term number. So the first term is 6. So I can just write that down. The first one is number 6. Now, what does the rest of this say? This other part is the recursive rule. It says, in order to get a term, right? In order to get a term in the sequence, it says, take the term that comes before it. So if you look at this really closely, n can be anything, right? N could be, for example, I could have the number 6 right here. And it says, in order to get the 6th term, take the 6 minus 1, or take the 5th term and decrease it by 10. So it's just saying, this rule just says, hey, to get a term, take the term that preceded it and subtract 10. Well, look, I want to get the next term in the sequence, and the term that precedes it, the one before it, is the number 6. So I just take the number 6, and I take away 10 from it, and it gives me the number -4. In order to get a term, take the term before it and take away 10. Oh, -4 minus 10 would be -14. To get a term, take the term before it and take away 10. The fourth term, it's going to be -24. So there we are, using the recursive rule. Remember, the recursive rule always needs 2 things. It has to tell you a recursive definition, has to tell you where you start, right, someplace on the sequence, and it also must contain the recursive rule. How do you move forward? How do you get additional terms in the sequence? And I hope it's really clear how to read this, right? There's a relationship between n and n minus 1, and it is, n minus 1 always is before the n. All right, let's move on to question number 5. So the 3 angles, right? This is a triangle angle sum theorem. The 3 angles in a triangle have to add up to 180. So I could say 3x plus 3 plus 131 plus 28 must equal 180 degrees. And if I collapse this all up, I'm going to get, 3x plus 3 equals, that's 159, 160, 161, 162, I think. So it's 162 equals 180. So I need to take 162 away. 10 minus 2 is 8. 7 minus 6 would be 1. So I get 18. Looks to me that 3x is the number 18. Therefore, x is just the number 6. So x is 6. All right. By the way, I could check that. 3 times 6 plus 3, right? And then plus 131 plus 28 better equal 180. This one, you can see that this is a right triangle, and I've got a right angle. These two smaller angles right here are the acute angles in a right triangle, and because this is already locking up 90 degrees, it's just a fact that the two acute angles, right, have to be complementary. Complementary. That means that if I add these two acute angles up and they are complements, they have a sum of 90 degrees. So 6x plus 2 plus 40 has to equal 90. Therefore, this plus 42 is 90. Um, let's see, if I take away 40, if I take away 40, that's 50. And then 50 minus 2 more would be 48. So 6 times x equals 48. And if I divide by 6, I get that x is the number 8. So x is 8. Great. All right, down to the last set of questions, and I think there are just the two here. And it says find the recursive. Oh, that's great, because question 4 up above helped me kind of review that. Recursive formulas. So there's two things, right? We can have a geometric sequence, or we've looked at arithmetic sequences. Arithmetic sequences are characterized by just adding or subtracting the same value again and again and again, whereas geometric ones are characterized by multiplying by the same value repeatedly. Well, if I look at this sequence, to go from 21 to 121, and then from 121 to 221, and then I'm adding the number 100 each time. So my recursive rule is going to take that into account, that I just keep adding 100. The other thing is that my first term is the number 21. So I think I could write this down, and I don't think the order matters, but I can say, hey, the first term in this sequence is the number 21. And I think I'll follow the pattern from question 4. I'll do this. I'll say, in order to get a term in this sequence, right, in order to get any term, an nth term, what you need to do is take the term that comes before it, the n minus 1 term, and you need to add to that term the number 100. And there it is, right? Every single term, as I move forward in the sequence, the next term is the previous term plus 100. I think we've also written these this way in the class. We've said something like, hey, if I want to get the next term, I like this notation better, I think. In order to get the next term in the sequence, take the term that you're at, or take this a term. In order to get the next term, take the last term that you have and add 100. And those both say the exact same thing. The important thing is here is, what's the relationship between these, between n and n minus 1? Well, if n was the number 6, this would be the number 5. And what's the relationship between n plus 1 and n? Well, if this was the number, it's the same, isn't it? If this was the number 6, whoops, without a green highlighter, if this was the number 6, 8, that would be n plus 1. That means n would have to be the number 5. So the important bit here is they're kind of this positional relationship, right? 1 is the previous one plus 100 more. So either one of those would work as the recursive definition. Okay, let's look at the second one. We're asked again to write down the recursive rule for this. And as I look at this, I can see there's a doubling going on here. But what's tricky is I'm not multiplying just by 2, because the signs keep changing. So I'm multiplying every single time by -2. So same thing, right? I'm gonna write down what my first term is, and in this case I could say my first term is the number 3, and I'll just say, in order to get to a term, take the term that came before it, right? Take the previous term and multiply that value by -2. So there's a very nice looking recursive definition, right? To get to a term, multiply by the number -2. Now, you know what? It's a nice time to review this, and we should look at this real quickly. What if you were asked to come up with the explicit rule for these? Well, in this case, the explicit rule is in this pattern, right? Y equals AB to the x, but I could use different notation. I can use like t of n. I can say something like this: t of n is equal to, now I need the 0th term, that's what a is. And in order to get the 0th term here, I would have to, instead of multiplying by -2, I'd have to divide by it. So I'd be looking at 3 divided by -2. So this would say my 0th term is 3 over -2, right? And to move forward, I'm going to multiply by -2, but I'm going to keep doing that as I move forward. So I'm going to raise that to the t power. So this is the explicit formula, right? Each time I move forward, I'm multiplying by another -2. Now, this formula, if you wanted to know like the 50th term, you just plug the number 50 in for t and it tells you. That, whereas the recursive formula, you've got to build up to the 50. In order to get the 50th term, you have to know the 49th term. To get the 49th term, you have to know the 48th term. Is that long regress? Since we're here, let's write down this rule also. So this is a arithmetic sequence, so I could say t of n. I'll do t of n equals, and then let's see, if I want to move backwards, I got 21, and I need to take 100 away from that. And yeah, it's late. 100, and I'm going to subtract that from the number 21. So when I do that, I get mass confusion. That's just 21 minus 100, Roberts. That's 80 and 1 less than that, right? So it should be 79. Why am I off the screen pressing calculator buttons? I don't know. It is 79, so, or negative 79. So my 0th term is 79. That's like my y-intercept. And then I could say plus 100 times n. And I could write this in the other order too. You probably would like that better. Every single time I'm adding 100, so I'd say 100 times n minus 79. So there you can see, that's nice. So these are not the recursive rules. The things I boxed there are the explicit rules, right? The ones where you just put in the one you want and it gives you that value. Whereas the recursive rules, you need to figure out, you figure it out by knowing where to start and how to proceed to other terms. All right, so that's the end for part C.